Hi guys, in this video I want to talk to you about work. I'll introduce it with an example and then I think I'll do some more examples with you later. So just high level, big picture, what is work? It is another way of looking at what we've already done. So we've already looked at energy changes happening in systems, and we've kept track of them with LOL diagrams. And that was if we put everything in the system, then energy changes would just be going from one part of the system to another. But what if everything isn't in the system? That's the basic idea. Work is when stuff from outside the system is interacting with it. And again, the system is something we choose. So there's a lot of choice happening in here. There's an analysis that can happen when we have everything in the system and when things are outside, and these two things should agree. That's the high level big picture. So let's see what that looks like. And here's an example, person throwing something up. I want to focus on 3 different snapshots. So here it's at the low point. Here the ball has some initial velocity and it's like a little bit higher up. And then here the ball is at its max height. So a little bit of good practice right here. What does the LOL diagram look like for this scenario? Should pause the video and try it. The ball, earth, and person are in my system. So what does this look like if everything is in the system? Pause the video, try it. Hopefully tried it. Initially, this is just chemical energy. In snapshot B, the middle one, this is kinetic. And in snapshot C, this is gravitational. If you put gravitational here in snapshot B, that's okay. For the purposes of this example, I want to keep things simple and just ignore this change in height and basically say like it didn't move up that much. So I'm going to ignore gravitational there, just for the purposes of this example, to kind of keep it neat and clean. In terms of equation, this is E chemical is equal to EK, and then that's equal to EG. This is when everything's in the system. What about when I take things outside? What does that look like? So this is just the ball, nothing else. At snapshot A, there is no energy. It's not moving. There's no gravitational. There's no elastic. That didn't change from A. But now I can't put chemical in because it's not in the system. The person's not in the system. But at B, there is still there's still kinetic energy. The same amount of kinetic energy as before. So where did that energy come from? Well, it came from outside your system. And this is what we call work. Equation-wise, this would be W is equal to EK. Notice that in snapshot B, at the later moment, there's more energy than there was at snapshot A. Therefore, we say, by convention, that the work done is positive. So this is positive work. I'm adding energy to the system. Let's look at snapshot B to C. So snapshot B to C, this is snapshot B, this is snapshot C. B, again, the ball has some initial velocity, and C, it's at its max height. So snapshot B is going to be the same as before, but snapshot C, there is no gravitational. And there isn't any kinetic like there wasn't before. There's no springs. So there's no gravitational because gravitational energy is an interaction. You need the ball and the earth in order for there to be an interaction. Otherwise, the ball by itself doesn't have any interaction energy. So where did this energy go? Well, it left the system. We call that work as well. Except in this case, we say that it is negative work. So EK minus W is equal to 0. The simpler way to write this equation is EK is equal to 0, or EK is equal to work. The signs, I don't want to focus on the signs right now, so let's just kind of gloss over that. It'd be helpful to just look at some examples to understand the signs better. But for now, intuitively, I started with some amount of energy, and that energy decreased. Therefore, energy left the system. And by convention, we call that negative work. To summarize, What is work? It's energy transferred by forces external to the system. It's positive when energy is being added, and it's negative when energy is leaving the system. The equation for it is this, and I'll try to motivate that in just a moment. So this is W, the work done by a specific force, is equal to that force times the displacement times cosine of theta, where theta is the angle between them. We'll look at that more in detail. I want to just highlight right now, there can be like the overall net work done, the overall energy added or leaving is equal to the overall force, the net force times the displacement. So you can apply this to specific force or to the overall. Conceptually, it's probably easier to think of it overall. What's the overall thing happening? And I want to highlight, basically, if there's no displacement, by the physics definition, there is no work done. So if this thing was like super, super heavy, and I'm using up a lot of energy to, hold it, really that's just my body doing chemical stuff, and that's like going into thermal. It's my body's heating up, but I'm not transferring any of that energy to the book. It's staying at rest. Kinetic is still. That's not changing. So I would not be doing work by just holding it. I'd only be doing work when I add energy to it by like throwing it or something. All right. I said something before that work is another way to look at what we've already done. So analysis 1 is everything in the system. Analysis 2, stuff from outside the system is interacting. Those two analyses should agree. So if you can recall the LOL diagram when the ball, when it's just the ball, was this. The equation was EK is equal to the work. And this, when the ball and earth are in the system, is EK is equal to EG. So what I'm trying to say right here is physics should agree. It shouldn't depend on what my choice of system is. Things should agree, and work is equal to EG. That's how these things work out. So I said my equation was force times displacement. Again, I don't want to worry about the sign right now, but yeah, I'll talk about the sign later. So just right now, I want to focus on just the force times displacement. In this case, it's Fg times your change in height, and the force is just mg delta h. I don't worry about the sign right now because it seems like if I were to plug in cosine of theta, I would get a negative, and I know to ignore that. Like I know I'm not being careful right now, so sorry about that. So kind of like what I did with forces, I know when two forces point in the same direction, they should have the same sign. I know now that when energy is being added to the system, the overall sign of it should be positive, and if it's leaving the system, the overall sign of it should be negative. So that's why I introduced the sign afterwards. I don't really worry about it so much in the math. I kind of force it to work. But getting back to the force times the displacement, we got mgh, and we know that gravitational energy is mgh. We can look at this graphically also. So when I look at the force of something that's in the air, gravity doesn't change. So if I'm plotting force sort of versus distance, that's going to be constant. And the area here, hopefully you should see, this is mg. So this area corresponds to the change in gravitational energy. It also corresponds to the work done. So force times displacement is work done. That's not just with gravity, though. It's also with springs. Recall that for the force of a spring, and x is the sort of the elongation or stretch, k is your spring constant, and the spring force was equal to that spring constant times x. So the area here is 1/2 base times height. It's a triangle. 1/2 kx times x, which is 1/2 kx squared. And that corresponds to the potential energy of a spring. Another way to look at that, though, is it's the work done on the spring, or the work done by the spring. Basic idea, when force and displacement are graphed, the area there will correspond to the change in energy of the work done. So that's the basics of work. I'll do some more examples in another video. Hope that was helpful.